voltage and reactive power control in power system. And we began our interaction with a basic one electric circuit, a single phase circuit with sinusoidally varying quantity Vm sin omega t applied to a inductive load R plus j omega L, and the current resulted naturally in this is having a lagging concept which is outlined in the description. Let V be Vm sin omega t, the current possible in inductive circuit being like Im sin omega t minus phi, a lagging angle phi is associated, and cosine of that stand as a power factor lagging. That would be the scenario. Now what is that exactly power as such this circuit is given with? That is instantaneous power P is V into I. Instantaneous, you must see lowercase letters are referred as instantaneous, V into I, and on whose substitution Vm sin omega t, Im sin omega t minus phi, and subsequent simplifications. The instantaneous power can be separated into two terms. The first term being the real instantaneous power, the another being reactive power. We all very clearly know this reactive power is very important. It is an oscillatory power to and fro, moving from source to load, load to source continuously. But the one active power is being consumed by the gadgets or equipments to perform their intended application. So therefore, these two powers are very important for us because there is a lot of consequences connected to which. When we find a real power mismatch, it affects our frequency. When there is a reactive power mismatch, that affects our voltage profile. It means to say, even though it is not significant, but it has a significant impact on profile of the voltage. Therefore, for the steady operation, the stable operation of the power system is considered. The active power delivery, reactive power delivery to a system must be considered as an important aspect. That is our beginning, how that reactive power comes into picture. So, reactive power can be given by a complex notation as S. Normally, many of the books refer the complex power as P plus JQ, where P become active power part of the representation and Q become reactive power part of the representation, which is also written as VI conjugate. If I know the representation of the voltage and current and it's a conjugate, VI conjugate, when I write, definitely this is going to split that power into term 1, term 2 like that. So therefore, this is how a complex power can be represented, the S equal to P plus JQ or VI conjugate. So then I have a reactive power triangle to make you all are aware how this reactive power makes the things different. When we have a system, definitely the hypotenuse of this triangle, if you could see the apparent power, which is S equal to V into I, RMS voltage and RMS current. The adjacent side to the triangle is an active power with the opposite side to the angle phi, which is being reactive power. Together reflect the apparent power of system. So, knowing to the system and its representation, system is highly resistive, system is highly inductive, system is highly capacitive. The representation of the vertical side, reactive side change. If this particular diagram is focused to you, this is a highly inductive system where the reactive side is vertically shown upward. This is highly inductive system, which is Vi cos phi along the adjacent side, Vi sin phi along the vertical side, and hypotenuse being P square plus Q square under the root as Vi. So therefore, if I find the capacitive circuit, definitely this vertical side which we have shown as the reactive power go downward. Doesn't matter for our relationships of triangle. Hypotenuse remain hypotenuse, adjacent side remain adjacent side, and the side which is opposite to the angle remain opposite side, but reactive negative, which is going downward. So this is how where we get this kind of representation. It is being revisited for our recall. Then I have generation and absorption of reactive power. Who do really generate reactive power? and who will absorb reactive power, why we should do this transaction. We are very much aware that for the power system operation and control in a steady and safe operation, delivery of active and reactive power to the end user is very necessary at specified terminal voltage and particular bus voltage. Definitely, it cannot be transmitted, it cannot be generated and transmitted like active power. That's the first thing we should keep in mind. Reactive power is basically generated by synchronous generator. We all are aware that synchronous generators are basically meant for active power generation to meet the requirement of the loads. Apart from that, they have an ability to develop reactive power to pump into the grid depending upon its capability. So therefore, when we have a synchronous machine which is going to operate over a wide range of excitations, when the synchronous generator is under excited, over excited, what we can say from that perspective, it is having an ability to make out the reactive power pumping or absorption carefully from the point of excitation, which is apart from active power what it is being dumped into the grid. So therefore we can say an under excited synchronous generator absorbs reactive power. It will absorb the reactive power whenever the excitation is under excited. When it is over excited, leading in concept, definitely this is trying to pump reactive power along with the active power to the grid. Then the wide range of excitation mode of synchronous generator only makes the basic substitute of required reactive power in the electrical power system. This is a natural phenomena. Having just controlled the excitation requirements of a synchronous machine, we can make out of the absorption or generation of reactive power, which you can see from this representation, single line representation. A synchronous generator is represented as a voltage magnitude behind the reactance, which is connected to a bus at a voltage V and injecting a current I, and it is delivering to a load P and Q. It is going to deliver P and Q. You can see from the diagrams, which two vector diagrams are shown to you, the terminal voltage of that synchronous machine's bus where it is connected V, and the current what it is injecting to the grid is lagging behind the voltage by an angle phi. And you can see the construction of the vector diagram having resistance is 0, the current and the particular reactance you can see perpendicular to each other, I into XS, the inductive drops V and inductive drop constitute the internal voltage of the generator. So you can see this kind of lagging definitely make absorption of reactive power. Here you will find injection to the grid. You will find the current is leading where voltage is horizontal, current is over which an angle phi leading. Then definitely I into XS perpendicular to this side joins over here. You can see the voltage profile of this requirement is very low in magnitude. It means, it doesn't mean that diagrams are not proportionate. There is a need to understand what exactly inductive load refers. The demand of that is higher terminal voltage and higher pumping. The magnitude of E should be larger than that of magnitude E over here when it is with a leading concept, because of the inductive drops which are very lesser in magnitude. So that makes the difference, and the terminal voltage what it is pumping with the voltage is different. So it's called voltage profile. So when you say inductive load, definitely requirements are different, losses and meeting up of reactive power compensation become higher for that. Here lesser the compensation. So invariably we say synchronous generators are the basic source of generation of reactive power apart from the active power. There is a term at the footer you can see. The capability of synchronous generator is to continuously supply or absorb reactive power is limited by the field current, armature current and end region heating limits. So I cannot simply take an advantage of making highly overexcited and keep compensating the required reactive power of the system from the synchronous generator itself is not possible. That's because of the limitation of field winding, limitation of the armature current and other associated phenomena which would result the failures subsequently. Therefore, it is an associated ability of the synchronous generator to produce reactive power along with the active power for the contingent requirement. But it cannot be a dominant requirement to be a dominant requirement that it is going to fulfill. It is not like that. So therefore, it is how one example you can see a 200 megawatt generator, suppose working at 0.8 power factor, having 10% stability allowance. It is observed for the stability aspect within the 10% permissible range. Observed that a 200 MW generator has a capability of producing 45 MVAR at full power output just by controlling the excitation requirement of a synchronous generator. A 200 megawatt generator which is pumping 200 megawatt to the grid have specific ability to develop 45 MVAR reactive power along with this capacity at its full power. This is inherent capacity of that. So we cannot improve or increase this beyond the specific capacity possible because this is the limitation of that machine. Similarly, I have the phasor diagram which we have seen. Suppose it is a synchronous generator is working at unity power factor. How is that? The vector diagram of that is represented. This is not the scope of us, but still when it is working in phase, how we can see this? The IARA drops of that synchronous generator, armature drops, IAXA synchronous generators reactive drop, and synchronous generator internal voltage what is generated here when it is UPF delivering to a resistive load, delivering to a lagging load which we have seen the terminal voltage of that V line voltage. You can see current is lagging behind that by an angle theta in this lagging behind, and IARA drop you can see parallel to this IARA at the vector tip of the vector VL, and perpendicular to this vector there is a IAXA, and when I join this it will become internal voltage of that considering resistance also. In this case resistance was ignored, so here it is considered. Then I will have at the tip of the vector VT or VL IARA which is parallel to current axis and perpendicular to that IAXA because inductive which is perpendicular to the current. So therefore it is representing the total voltage, and here you find interesting fact, power angle delta you will find here. Delta is the angle between the terminal voltage and internal voltage of the synchronous generator. This play a vital role for our transfer of power from bus 1 to bus 2. That is what is called power angle study of a synchronous generator connected to a bus when delivering power. This angle has to be as narrow as possible, so to make it profile, and we have seen this maximum when is that like that. So therefore this is for lagging concept. Similarly, when the terminal voltage VT and a current which is shown to you as leading, respect to shift in diagram you will find. So VT at the tip of that IARA parallel to current axis which is current leading by an angle theta, and IAXA you will find. Then you will find profile of the voltage easily. What is exactly observed by you here is when the system is highly leading, power factor is very superior, the terminal voltage maintained at the synchronous generator to deal that megawatt is very nominal, which has to serve very effectively and easily. When the same synchronous generator working at a very lagging power factor situation, you can see the magnitude of the side which is very dominant here. It has to overcome these all drops and oppositions inside. Hence this is like this. And when it is resistive load, you can see a comparative change here. Therefore, always a system with a UPF or leading is preferable, but we cannot make out of that as the system real time in the world is inductive in nature. It has to balance both. So these three are diagrams which just give you an insight how that vector diagram of a synchronous generator at three different power factor conditions, UPF, lagging and leading, makes the magnitude of the generated voltage different from each case in that. Now moving to another aspect. One is synchronous generator, where we have an option of generation and absorption of reactive power. The second is overhead lines, the transmission line, where we generate electricity at resources, however they are scattered around the geographical periphery. To transmit it to the load center, we go for overhead transmission line, and those transmission line have a characteristic impedance given by root of L by C, and this L by C definitely makes a difference. Just a minute. Yeah. So where L is the inductance of the line and C is the capacitance, shunt capacitance of the line. The natural loading, we call it a surge impedance loading, SIL is V0 square divided by ZC. That is what is highest possible power it can deliver. Definitely, when the system is highly inductive, moreover, transmission lines itself possess inductance and distributed capacitance throughout the model, whatever the transmission line, long you refer or medium with the pi and t you refer. So all those parameters L and C definitely matter. Along with the system to which the power being transferred over the transmission line possess highly inductiveness, highly capacitiveness depending upon the situation. We have a situation, highly loaded system, ill conditioned power system do suffer from sluggish and lagging power factor. Then the overhead line, highly inductive, suffer from absorption. They absorb the reactive power because of its highly inductive in nature. They keep absorbing reactive power. Because of that higher absorption, systems suffer from the inductiveness. When the system becomes highly inductive in approach, overall power factor of the system falls. Operation of the system having sluggish power factor becomes very challenging and adverse. We all very clearly know poor power factor result higher current requirement, then higher losses, pulsations, all other associated adverse effects of poor power factors are noticed. Hence, overhead line as a part of highly inductive in nature do result that because of the inductance part of that. Suppose the overhead lines were highly capacitive, load is suddenly rejected. Let's say highly inductive load delivered by a transmission line, load is suddenly removed. The total current flowing on the line become leading because sudden cut of load make the profile of the voltage very leading. Then I would other way quantify overhead line whenever their inductive reactance dominate over the distributed capacitance of that, they start absorbing the reactive power. Whenever the capacitive reactance of that line is dominating on the inductive reactance of the overhead lines, definitely the leading nature is noticed, the absorption of reactive power is very less at that time. Other way, if you just see a notation here, condition for a overhead line to absorb reactive power from the system in endeavoring its duty is XL being over the XC like this way, greater than XC, at that time it is going to absorb the reactive power. Then who has to supply this reactive power? It become a burden on the generating system. If I do not have any compensating mechanisms initially, the reactive power has to be delivered by a source, the source being synchronous generator. But synchronous generator have a limited scope to generate because that is not the significant role of generation. They are meant for active power generation. So this cause a bottleneck issue in the operation because there is an indirect demand of reactive power by the overhead line because they being more inductive in its approach or operation. How that is XL greater than XC, XC less than XL can be a different scenario. There could be highly inductive loads connected to the system, whole system together becoming highly inductive, or loads are declining in nature, inductiveness is diminishing, or loads are compensated by capacitive concept, would be other way. Therefore, the capacitance and inductance model of the line matter, or to which kind of load this particular line which is highly inductive delivering the power also matter. So on that basis we need to say overhead transmission line become a competent absorber of the reactive power whenever it find its inductive reactance is dominating on the capacitive reactance of it itself. And overhead line do contribute to produce reactive power to the system if required whenever it find its capacitive reactance dominating on the inductive reactance. There could be a scenario when is that transmission line which is a overhead line able to provide reactive power then. That is a scenario over here. Imagine a highly inductive load is being served by a transmission line. Load is suddenly cut off which was carrying a very highly inductive delivering inductive load, and load is removed. Suddenly the current which was lagging while delivering that load slowly changes to its nature to improving. At that time the distributed capacitance model of the transmission line override. That XC capacitive reactance of the line dominates on the inductiveness with which it was delivering the power at that time, because the removal of load may make it more reactive by capacitance. At that time the reactive power what is there in the system or on the line can be a substitute to the reactive power. In this way the role of overhead line change depending upon its reactances. So that is how the current power electronic technology FACTS, flexible AC transmission approach, which is working to modify the reactance of the transmission line itself. That is, we cannot change the transmission line, but we can change its characteristics. The inductiveness can be compensated by adopting alternative capacitive concepts by making it more reactive. Then the adoption of such mechanism make the overhead line intelligent. Whether they are absorbing or they are delivering is managed by such additional incorporations. Next, underground cables have another opportunity. When we have underground cable, UG cable what we call it as, definitely when we say UG cable, it is not an ordinary cable like a central conducting element and an insulation. It is definitely having different layers of insulation and armoring and outer sheath or cover. That is having a different coating and covering to provide mechanical strength as well as insulation to the conductor at the central. Therefore, because of that structure of different layers of insulation around that conducting element, when this conductor is buried into its operation, put into operation, has an opportunity to generate the reactive power. That is what is noticed here. When I have transmission line which I was showing you with a particular distributed transmission line model, how it is going to dominate in this earlier case. Now similarly I have the underground cable. A 275 kV cable is having an ability to produce 6.2 to 7.5 MVAR per kilometer length of its run when loaded below rated value. Definitely when for the modernization or the technological implementation of service lines or overhead lines into underground cable, definitely this become an opportunity to put into underground cable. And a special case study from US continent. This example is taken from US GLQSIC From that textbook it has been taken. A 275 kV underground cable has a capability to produce 6.2 to 7.5 MVAR per kilometer length of its run when it is loaded below the rated value. This ability is because of the distributed capacitance between the different insulation levels of the conducting material and insulation of the cable. That makes an possibility of production of reactive power. Can it be a continuous element to produce? Definitely no. It is a marginal change in operational aspect can only make it as a minimum delivery possible. But it is to see when I am operating a power system, where do this reactive power is resulted from? Root cause of that, if you would like to understand, these are the corners we get encountered. There is an generation of reactive power in the system, even though we are not doing, it is happening because of the nature what it is being with the implementation. So therefore, underground cable, whenever they are loaded, loaded lesser than their capacity, they always have an ability to produce reactive power. When they are overloaded, definitely the inductiveness of that might dominate and it would be nominally like absorbing the reactive power. When it is underloaded, we have an opportunity to view that there could be a possibility of generation of reactive power from the other end. Then we have transformer. As the name says, transformer, highly inductive in concept by the principle itself, incorporating inductive elements and core. So definitely it absorbs reactive power and irrespective of the load it is delivering. So transformers in a system always absorb reactive power. I square X can be one of the general equation we can write. Similarly, loads. When I say loads, loads normally absorb reactive power depending upon the type of the load. Load is inductive, it should absorb for its activity concerned. And heavy or lagging load cause severe drop in voltage. This is a phenomena we were very serious about that. P and delta relationship, Q and V relationship are very peculiar in the power system. Any imbalance in the active power will affect the frequency. Any reactive power imbalance will definitely cause changes in the voltage. The voltage flicker, voltage drop, that kind of profile observed in the voltage will definitely reflect the balance of reactive power itself. If it is able to cope up with the terminal voltage what it is specified, it is say system is having inherent capability to retain the terminal voltage, it is to say reactive power balance is possible. If the system is suffering voltage drops, voltage collapse in a very serious term, rapid drop of voltage due to rapid load or rapid change in load on the system, that kind of phenomena we call it a voltage collapse. Collapse in the sense suddenly falling to a very low value which cannot be controlled or recovered back. That kind of phenomena lead over a time. Once we see a drop in voltage, further drop as the load increases. So if the system is not able to make out that changes and adequate correction to the system, voltage collapse is possible. That will be studied as stability aspect of the power system. So loads as such, loads depending upon the type, they keep absorbing if they are inductive, and heavy inductive loads or heavy loads definitely cause major drops in voltage. Then the compensating devices, when I characterize, compensating device is either make use of power electronic, make use of capacitor, inductor and associated network, mainly meant to maintain the reactive power balance. As we were seeing, the very first element of generation and absorption of reactive power in the system is synchronous generator. The very next is compensating devices. These compensating devices are surely working with the intelligent computation algorithms or mechanisms, taking care of what right now the power factor, what right now the terminal voltage is, and accordingly they keep compensating the required correction to the either increment the tap of a transformer or add a capacitor or change the load or control both, however it is planned to do. So therefore, these compensating devices are the additional fittings, additional installation to correct the profile of the voltage in respect of reactive power. So these were the 5 or 6 elements which come under one good question. Explain absorption and generation and absorption of reactive power in the power system. You need to narrate 2 to 4 lines per each category of those things. And when I say transformer, there could be another option. Transformer always absorb reactive power was the one important thing we have seen. Other way I could see a transformer with a tap changer facility. It is another advantage of control of voltage. Facility with the tap changer shift the taps according to the required terminal voltage. That incremental addition or removal of voltage as required by the transformer taps makes the required voltage available at the terminals. Therefore, we have transformer with the tap changer facility perform that. And phase modifier, they come under the compensating devices, definitely work on the power factor and the phase angle associated with the requirement. So this way, these are the 6 key points we can take into account how absorption and generation of reactive power takes place in the system. Now moving to simple aspect. How do you control voltage then? Because we seen very carefully, reactive power reflect voltage. If you control the voltage, indirectly you are addressing the reactive power. In line with this, there is a strong connectivity between Q and V. There is a sensitivity with respect to Q and V one another. How is that worked out? The first heading for that is methods of voltage control. So the control of voltage at all levels is by the reactive power flow itself. That's the first statement. Why we are addressing the voltage? It is because of the reactive power need and necessity. Voltage is monitored as a parameter of its balance. Therefore, we need to control it such that the other parameter reactive power flow is worked out. While generating units are equipped with AVR, automatic voltage regulator, and other control methods are used throughout the system. So they are like someone. As we are aware, AVR, automatic voltage regulator, is one of the control loop associated with the synchronous machine to see to it that terminal voltage always maintain constant with respect to the set reference value by adopting excitation control. So by changing the excitation control, it is trying to work for the stable terminal voltage. Apart from that, we require additional control. We said reactive power cannot be transmitted over a long distance like your active power. That's because I square X drop is enormous, because whole system of generation to delivery is inductive in concept. Accumulated drop increase in quantum. Definitely we cannot pump that much of huge reactive power from the source itself. Therefore, the reactive power cannot be transmitted over a long distance. That is the first limitation. Then how it should be addressed then? At the needy point, it need to be compensated and worked out. That is the reason we have to learn the different methods to work on that, on voltage basis or on reactive power injection basis only. On the voltage control basis, following are the few methods identified. One is line reactance compensator. So we have seen the transmission line being very inductive in nature. Whenever the inductive reactance is dominating on the capacitive reactance of it itself, definitely it absorbs. That is what is seen. Whenever the load is thrown off, the distributed capacitance of that definitely become a dominating and improves. That's what the nature of the loading and unloading phenomena we have seen. Therefore, the very first concept under the voltage control is line reactance compensation. We have to see to it that the reactance of a transmission line XL need to be reduced By compensate, the word compensation means what? Work in opposition to that. So for that, what is being referred? Series capacitors are used for this purpose. You are very sure. If XL and XC, if you understand the single phase RLC series circuit concept, XL and XC are opposite to each other on a vectorial representation. Suitable compensation of XL can be done with the XC to cancel that reactive side. If the reactive side cancels off, the angle phi which results at the resultant become very narrow towards 0. So cosine 0 goes 1, power factor simply become 1 at that time. In that due respect, the line reactance need to be modified. This is the first method to control the voltage is drop of voltage in the system is only because of reactance of the system. This reactance need to be worked out by series capacitor is the first approach. The second is shunt reactors and capacitors, which act as sinks and sources of reactive power respectively. So when you focus only a transmission line, a very long transmission line, for that series compensation by capacitor if you incorporate, that may fulfill the requirement to an extent. If not, the alternative is shunt reactors, reactors hooked to the line to the ground and a capacitor from line to the ground, which act as sink and source for reactive power. As we were interacting in the earlier point itself, when a highly inductive transmission system or a transmission line delivering power to a highly inductive system definitely suffer higher inductance, because of which inductive drop is more, lagging concept is identified in that. To improve upon that, if I adopt shunt capacitor, which will improve the nature of the power factor of that particular current flowing on the line. So use of shunt capacitor is also another concept at the point of load. At the point of load, suppose there is a delivery of power from bus 1 to the bus 2. Bus 2 is highly inductive. Load is highly inductive, system is very good. So when the load get connected to the delivery system suffer because of the load nature. So compensation shall be at the load side only. That is how a shunt compensation at the load side itself it is worked out, which will substitute or provide necessary leading volt ampere. Leading volt ampere at the point of requirement itself, that will compensate the required reactive power, and transmission system finds effective control of the power flow over there. That's how when there is a need of reactive power at a particular load itself can be focused to compensate using shunt capacitor at that point. Or if the suddenly highly compensated system, just imagine a long transmission line, the first case itself we can consider. A very long transmission line having series capacitor and other controlling concepts meeting the requirement highly compensated. Suddenly load is removed. What will happen? The highly compensated line suffer immediately because it was a compensated the reactive thing and it was making the things to work. Suddenly load is removed, the overcompensation is viewed very immediate to the removal of the load. Highly overcompensated systems are very dangerous. They affect the operation of the system itself. And how you work it out? By hooking shunt reactors from line to the ground. So these reactors start absorbing the leading volt ampere which are available on the system to balance the requirement. Hence, I would say the balancing of that particular leading volt ampere has to happen from inductors only. Hence, inductor and capacitor have to be the part of the compensation system. The second method says use of shunt reactor and capacitor which act as a sink or source to the reactive compensation has to be applied. The next is synchronous condenser which can act as a source or sink of reactive power. So a synchronous condenser itself is a synchronous machine, or you can view as a synchronous motor. Let's see a best example for this synchronous condenser is synchronous motor with no load on the shaft. It is simply running with the three-phase power and fed with the both stator and rotor side. It is running, and the excitation need and necessities of that. I am speaking very carefully. Synchronous motor running without any mechanical load on its shaft. The excitation control of that is managed such that it is able to supplement overexcited, and it is able to absorb when it is underexcited. Such a synchronous condenser can fulfill our required reactive power into the system or absorb from the system, so that voltage control is possible. See, we are tackling from injection or absorption perspective, such that their effect is to see that voltage is always at the superior level as expected or within the range. The another method is regulating transformer like a tap changer or other booster transformer. We will see them into the methods. So this is nothing but application of transformer. When I say a transformer, definitely it shifts the voltage or shifts down the voltage, or it boosts the voltage using booster concept. So that is going to work directly at the voltage point. So we are getting the terminal voltage at the secondary from the primary by having shifted it up by a proper tap ratio, or added by a voltage or removal of the voltage by booster concept. So this transformer make use of reception or receiving a side voltage as comfortable to the requirement. The last mechanism would be power electronic based flexible AC transmission system, FACTS, controller and custom power devices. So as we were discussing in the earlier point, these are the new evolutions in current trend. So these are smart devices with the state-of-art design, intelligence, able to work, think and act on the scenario very intelligently, but they are very costly. They make use of what? Basic element, reactors and capacitor and associated circuitry and controls, such that this intelligent program or controllers will see the status currently, set point what is required, and how to achieve and track it properly can be done. So these are the very smart things right now working, but very costlier in approach. So invariably, if I see a simple system, just before closing our session, a simple system, single phase system, as earlier we have seen, a single phase representation of the three phase system E, and a load, I mean internal path representation R plus Jx, and a load here. So this is load. So transmission line, the generator and the load at load voltage, P plus Q is the delivery, whose vector diagram can be represented from the terminal viewpoint. If I have terminal voltage V, P and Q are my requirement. Suppose I is the current flowing and E is the generated voltage. How is that? Profile of the generated voltage is represented from load voltage perspective. How is that V is being maintained by this generator at this terminal? What is that voltage at that time? What is the power angle between these two? How the swing happen between these two? We can just get by this representation. For this, what we'll be doing? Terminal voltage is a reference. You can see here OA. OA refers, a vector OA refers terminal voltage. Then there is a drop I into R, I into X along the transmission system. You can see IR drop is in phase with the voltage. You can see at the V, at the edge A, at the point A, vector IR is drawn parallel to current axis. So VI refers to a system voltage, which is a receiving end and a current. In parallel to this I have IRA. Then in quadrature to that, in perpendicular to that IR, I have I into X. We can see here, from perpendicular position of this, it is shooted upward like this. Then if I join that, that becomes OE, the internal voltage or the voltage of the synchronous generator. And if I analyze this carefully, the angle between the generator voltage and the bus voltage, this becomes power angle. This play a role. When is that? Maximum power transfer takes place, etc. will be seen on this basis of delta. Now, from this perspective, there occur our study starts. So, having seen OA as a vector of terminal voltage, current lagging behind the voltage for the inductive system, and IR and IX being two drops, IR, IX, we can construct this vector diagram. Then I can construct few points, projection, dotted line you can see as a projections. If I extend this OA further like this up to C, and if I drop a perpendicular from E downward like this, then drop a perpendicular from IR point to this vertical to the horizontal line at B, at E, you can see a small construction. Basically it was OA, IR, IX, OE. Dotted line show you additional projections, extensions, and we can label. So AB as a new term, BC as a new term, DE and CD as a new term for our representation. How is that? So you can see an angle lagging phi with this IR with the AB here, and that angle automatically reflect as angle between this side CD and this lateral side IX. This become an angle. So with which we have a lot of relationships to be established. So this vector diagram become basic for us. Later we can draw conclusion that the projection of this particular side, IX side, horizontal and vertical and horizontal, and IR sides projection or horizontal axis become AB. So I can write delta in phase magnitude, voltage magnitude delta Vp and delta Vq quadrature component. We want to develop relationship between a small change in voltage in phase, voltage in quadrature. So to get them, this vector diagram need a correction. This will do in the next class. I have again same diagram and same dependence I would like to